Hi, I am Sanjay Patel. In this lecture, we are going to see some examples of principal ideal ring and principal ideal domain. What is a principal ideal domain? That we have understood in our previous video. But let us recall an integral domain R plus dot in which every ideal is a principal ideal. Then it is called a principal ideal domain. So I can say R is P.I.D, that is principal ideal domain, if and only if for every ideal capital I in R there exists some element A belongs to R such that the ideal I is generated by the element A. In other words, every ideal is principal ideal. So if you want to show that an integral domain is a P.I.D, that is principal ideal domain, just start with an arbitrary ideal I and show that that ideal I can be expressed in this form. Means that ideal I is generated by some element of the ring. Okay, let us see the first very important example of principal ideal domain, and that is we are going to write as an important result or a theorem. So this is my first result. The ring of integers z plus dot is a principal ideal domain. Okay, we know that the ring of integers is an integral domain, means it is a commutative ring with unity in which there is no zero divisors. Okay, let us prove. So to show that it is a principal ideal domain, first of all, we note that the ring Z is an integral domain. Let us start with an arbitrary ideal in Z. Let capital I be any ideal in the ring Z. Okay. Now I is arbitrary ideal, so there are two possibilities. This implies I is either a zero ideal or it is not a zero ideal or a non-zero ideal. Okay. If I is a zero ideal, if I is the zero ideal, then we know that we can write I as the ideal generated by the zero element. So therefore, in this case, I is a principal ideal. What we want to show that is every ideal in the ring Z is a principal ideal. So the first thing we have proved here is if it is a zero ideal, it is a principal ideal. Next, I consider a non-zero ideal in the ring Z. So suppose the given ideal I is not equal to 0. So this implies there exists some A belongs to I such that A is non-zero. Remember that this I is a subset of Z. So elements of I is a subset of Z. So elements of I are all integers. So A is also an integer and A is not equal to 0 means A is a non-zero integer. Now this I plus is a group, is a rather a subgroup, the subgroup of the group Z with respect to addition. So therefore A belongs to I implies I can say its negative element minus A also belongs to I. Now remember that a is an integer. So, and also it is not 0. So either a is positive or minus a is positive is clear. So therefore I can say either a or minus a is a positive integer. Is a positive integer because a is non-zero. We have already written that thing. So if that means the element, the set I has at least one non-zero positive integer. So now I define a set. Define a set, the capital S, as all those positive integers, all those natural numbers, say all those n belongs to n, such that n belongs to the set capital I. Then this S is non-empty because we have written that either A belongs to, means either A is positive or minus A is positive. And we know that A and minus A both belongs to I. So clearly S is non-empty set and S is subset of n. S is subset of n. So therefore by well ordering principle, the set S has the smallest element in it. Okay, that is, let us call that smallest element. Let me write in a different way, not this way. By well ordering principle, S has the smallest element, and let us call it, say, small m. Okay, and that means this m belongs to S and m is the smallest element. M is the smallest element of S. Let us call it star. Okay. What I will be doing here is I will show that the set I, the ideal I which we have started with, is actually an ideal generated by this number m. So let us recall what we have done. I want to prove that Z is a principal ideal domain or a principal ideal ring. So I start with an arbitrary ideal I in Z. If I is a zero ideal, I have shown that I is generated by 0, so it is a principal ideal. Now I assume that I is a non-zero ideal, and in this case also I want to show that this ideal I is a principal ideal. So I will be showing that this I is generated by some integer, some element in Z. So that element is the number small m. So let me write here. We shall show that the ideal I is equal to the ideal generated by small m. So let us start with one element from the left hand side or right hand side and show that it is in the other side. We want to show that these two sets are equal. Okay. So first thing, let X belongs to this set. That means X is of the form, say, R into M for some R belongs to capital R. Okay. Now this M belongs to S means M is also an element of I by definition of the set S. What is the set S? It is set of all positive integers which belong to the set I. So when we have written that M belongs to S here, so M belongs to I also. Okay, M belongs to I and I is an ideal. Okay, so therefore M belongs to I and R belongs to R implies R into M belongs to I because I is an ideal. Okay, so we are using that ideal condition. R belongs to R and M belongs to I. So product of these two belongs to I because I is ideal. But what is R into M? It is X. So X belongs to I. Okay. So what I have proved here? I have proved that whenever X belongs to this set, X belongs to this set, X also belongs to I. So thus, for every X belongs to this implies X belongs to I. And therefore, this set is subset of I. That is our first result. Now to prove the reverse inclusion, I start with any element in the set I and I will show that it belongs to the ideal generated by small m. So let us take X belongs to say I. X belongs to I, be arbitrary. I will prove that X belongs to the ideal generated by m. Remember that X is an integer. Therefore, X is an integer. Why? Because we know that I is subset of Z. I is the subset of the ring of integers. So everything in I is some integer. Also, we have the m is a positive integer. So I want to apply the division algorithm theorem for x and m for integers. I can say, therefore, by division algorithm theorem, we know from number theory, division algorithm theorem, there exist integers q and r belong to z such that I can write x is equal to m into q plus r, where r is the remainder, so 0 is less than or equal to r is strictly less than m. Okay, so this is an important statement. Now, from this, what I want to prove here is r is 0. So I claim that r is equal to 0. To prove this claim, let us assume to a contrary that suppose if possible r is not 0. So suppose if possible r is not equal to 0. Okay. So therefore we have 0 less than r less than m. Okay. And now from 1 we can write r is equal to x minus mq. Remember, everything in this equation is an integer. So x, m, q, r all are integers. Okay. And we know that this m belongs to I. We have noted somewhere. Yes. This m is an element of I. So what I can do is this. Now m belongs to I and q belongs to the ring Z, and therefore m into q belongs to I because I is ideal. I is ideal in Z. Okay, m into q belongs to Z. Also x belongs to I. That is what we have started with. This x is an arbitrary element of I. We have taken this x belongs to I. So now we have two elements in I. One is this x and other is this m into q. Okay. So therefore x minus m into q belongs to I. Because I is an ideal, therefore I is a subgroup of R plus, or I is a group with respect to addition. And this implies, I can say that R belongs to I, because x minus m cube is nothing but R. So what I have proved? What I have proved is this. We have proved that R belongs to I and R is less than M. We have noted that R is between 0 and M. So R is strictly less than M. So I have shown that there is an element R belongs to I and R is less than M. And R is positive integer. So let me write not R belongs to I here. What I have proved is R belongs to S. R belongs to S. I can say this implies R belongs to S. Why? Because R is positive and R belongs to I. R is a positive integer and R belongs to I. So R belongs to S by definition of the set S. So we have proved that R belongs to S and R is smaller than M. This contradicts result star. What is star? The star is this. Just a minute. We have written that M is the smallest positive integer which belongs, yes, here. M belongs to S and M is the smallest element of S. And what I have written here is there is something smaller than M in the set S. Or let me write this way. This contradicts that M is the smallest element of S. Okay, it contradicts the result number star. Okay, therefore our supposition must be wrong. Therefore our supposition must be wrong. What was our supposition? We have assumed that R is not equal to 0. So R equal to 0 is proved. R is equal to 0 is proved. Just recall that we have claimed that R is equal to 0, but to prove this claim, we have started with suppose if perceived R is not equal to 0, and therefore we are getting this contradiction. So it must be 0. So R must be 0. Once R is equal to 0, in result number 1, I can write X is equal to MQ. So this implies, therefore, from result number 1, I can write X is equal to M into Q. Where what is Q? Q is some integer, and I can say that this implies X belongs to the set M, because the ideal generated by M is set of all multiples of M, and I have shown here that X is a multiple of M. So thus, for every X belongs to I have proved that X belongs to the set M. And therefore I is subset of this set. This is my result B. So from A and B, what follows is I is equal to M. That is, I is a principal ideal in Z. That is, I is a principal ideal. So in any case, whether I is a zero ideal of ring Z or I is a non-zero ideal, we have shown that it is always generated by some element, or it is always a principal ideal. So thus, every ideal in Z is a principal ideal. So this implies the ring Z plus dot is a principal ideal ring or principal ideal domain, because it is an integral domain. So this is a very important example of principal ideal ring the ring of integers. Another important class of principal ideal domain is in this next result. Prove that every field is a principal ideal domain. Okay, the proof is very simple, and we already discussed in one particular example earlier. Let R plus dot be a field. So therefore it is clear that every field is an integral domain, we know. So R is an integral domain. R is an integral domain. And we know that a field has no proper ideals. We know that. So this is an important result we have proved earlier. We know that a field has no proper ideals. No proper ideals. That is, only ideals of the ring R are I equal to singleton 0 and I is equal to the ring R. So the field has only these two ideals. And in this case, if I is equal to 0, if I is the 0 ideal, then I can write this ideal as I as ideal denoted by singleton 0, I mean the 0 element. And if I is equal to R, then I can write I is equal to 1. And remember that field has unity because 1 belongs to R. So R is a field and it has a unity element. So the ideal denoted by 1 is nothing but the whole ring R. Okay. So therefore, every ideal of R is a principal ideal. So therefore, I can say that R is a principal ideal domain or principal ideal ring. So every field is a principal ideal ring or principal ideal domain. Okay. So it is a very easy and small result, but very, very important. Every field is always a principal ideal domain or principal ideal ring. And as a result of this theorem, we have so many examples of say principal ideal domain. The examples of principal ideal domain, just write down any field. So Q plus dot, then the set of real numbers. All these are fields, set of complex numbers. Okay, and Zn, comma plus n, comma dot n, where n is prime. These are all examples of principal ideal domain because all are fields. These are all fields. So we have seen some interesting example and results in this lecture about principal ideal ring. In the next lecture, we are going to prove the converse of the theorem that every field has, say, no proper ideals. So what I am going to show is if a ring R is commutative with unity and it has no proper ideals, then it is always a field. So till then, goodbye. Thank you.